Good afternoon to everybody on the East Coast here. Good morning to everybody else. My name is Jack Weeks. I work for GPM Hydraulic Consulting. This webinar is going to be for troubleshooting proportional valves. Largely, the information here is going to be on a Bosch proportional valve. Now, I don't want that to be taken as any sort of endorsement on Bosch valves or anything. We just had to kind of pick one. Bosch valves probably are the most common that we run into, we have the most experience with. But all the information in here will also apply to the other types of valves. The only difference will be that some of the numbers might change, and it would be a good idea if you're using some other type of valve to go to their website and download a spec sheet and things like voltages, impedances, and that kind of thing. If you want to make checks on the valves, use that. But the principles are going to be the same, regardless of the type. Now, you see over in the chat window, I've inserted a link where you can download some course material. You might want to download that to follow along, or you might just want to have that handy for reference for when you want to use some of the information here. We're going to show a couple of schematics and have some information that it might be handy to have in a printed form. You wouldn't be likely to remember. Okay, let's go ahead and get started. The symbol for a proportional valve is going to look a lot like a directional valve symbol. Directional valves, those are great as long as we want to move an actuator one way or another, or stop it or something, but sometimes we want to be able to control the speed, and we want to be able to control it electronically, and that's the primary difference between a proportional valve and a directional valve. If you look at the symbol, you see that this looks an awful lot like a solenoid, but it has an angled arrow, diagonal arrow going through it. That arrow could be pointing either way, by the way. It could be pointing up as well as pointing down. I just drew it pointing down so it wouldn't conflict with the solenoid symbol here. But solenoids are either energized or they're not. A proportional valve uses a coil similar to a solenoid, but this one's different because it can be partially energized, and we can shift the valve a little bit so that we can control the speed by controlling the flow that's delivered to the actuator. Long years ago, the only real option we had for that was a very expensive servo valve. Proportional valves started taking that over. They're not as accurate as a servo valve, but every year I see them get more accurate all the time. One of these days, they'll probably completely replace servo valves, but nowadays we only need to use the very expensive servo valves and deal with the maintenance nightmare of keeping the oil so exceptionally clean because of the tight tolerances there, when we need very precise control. And now the two symbols, one, the direct solenoid operated, and the other is the solenoid controlled hydraulically piloted. In other words, a two-stage valve. The direct operating valve has very small ports, and it's only used in very low flow applications. But if we have a lot of flow, we have to move a very large actuator, or we have to move something very fast, then we're going to need a lot of flow. We have to use a two-stage valve then. So we'll use a direct operated valve to pilot a much larger hydraulic valve, exactly the way we would do with a directional valve under the same circumstances. Now, the direct operated valve is a 4-position valve. You see that we have 4 squares right here in the solenoids, or in the schematic symbol, and these all represent positions that the valve can be shifted. This position here is called the fail-safe position. That's the position that will be shifted to by the spring if we have no signal at all. So if we don't have any power going to the valve coil, if we have a power failure, or if we have a loss of our enable signal, which we'll talk about in a little bit, then the spring, this symbol here indicates a spring, will shift the spool into this position, and in this particular fail-safe position, you see that all four of the ports are blocked. Right? That's going to block all the flow to or from the actuator. This symbol over here has the U and the S. It's actually a Greek letter mu, but this is a symbol for an LVDT. That's interested, it's linear variable displacement transducer, or some people call it a linear variable differential transformer. It's the same thing. Essentially what it does is it takes the position of the valve spool, that's illustrated by the S, and converts it into an electrical signal indicated by the U. And we'll talk a little bit more about that. That helps us achieve the accuracy that we need to compete with a servo valve. The way it works is by applying a command voltage to the valve amplifier, we can shift the spool as we want to. Now, if we apply a positive voltage, it's going to shift it toward this position here. The straight arrows we call the A position, and negative voltage will shift to the crossed arrows position, which you can see reverses the flow between the 4 ports. So if we apply a positive 5 volts, for instance, and for a lot of Bosch valves, they'll use a plus or minus 10 volt command range. If we put a positive 5 volts for a command signal, that will shift the valve halfway into its A position, delivering half of the available flow and moving the actuator at half speed forward. If we increase that to 10 volts, then it opens up all the way. Okay. Essentially, that's the operation, and with a negative voltage, it would shift it toward that B or crossed arrows position. This is what the valve looks like on the inside. See, here's the valve spool. This is the spring that we were talking about. This is the coil, or the solenoid. We will generate a current in here. The stronger current we generate, the more powerful of a magnetic field will be developed. The stronger the field, the more the spool will shift, opposing the spring. Now also notice a little tail on the end of the valve spool, and here we have a ferrous or iron core, and that is going to be centered between the LVDT coils, right? There's 3 of those, and we're going to talk about how that works too. But the output of this LVDT is delivered up here. So by measuring the output from the LVDT, we know the exact position of the valve spool at all times. If we don't have any enable signal or power supply voltage to the amplifier, of course, there's no current induced in the coil. The valve will stay in whatever fail-safe position it has. And you see this one has the closed fail-safe position, and that blocks all 4 ports. Our hydraulic motor symbol over here, with the flow blocked, our motor will not turn. There won't be any flow path into it or out of the motor. And here's our valve amplifier here. Our power supply is turned off. We don't have any command voltage, and we don't have an enable signal. Okay. When we turn the power supply on, then we get an enable signal. That closes this link here to direct our signal to the amplifier. The power supply is turned on, 24 volts is common, and that allows us to develop current in the coil generated by the amplifier. Once we get our enable signal and our power supply is available, then that's going to generate enough current in the coil to compress the spring just enough to move the valve out of its fail-safe position and into its center position. Right, now let's go back and look at the power off condition here. You see that this is the fail-safe, this is the B position, the center position, and the A position. Notice that the center position and the fail-safe in this particular valve are the same. So we've generated enough current in the coil, and for a Bosch valve, that's about 1.35 amps, to move out of the fail-safe position and into the center position. Okay. At this point, if we apply any command voltage, then we will be able to move from the center position into either the A or B position. If we apply a positive voltage, that will increase the current in the coil and move us toward the A position. If we put a negative voltage on here, it will decrease this current. The spring will push us toward the B position. So the spool shift is going to be more proportional to the command voltage. And we show on this graph right here, you see that the higher positive voltage we apply, the farther we go into the A position. And the higher negative voltage we apply, the farther into the B position. So as an example, if we apply a 6 volts, positive 6 volts, that will shift the valve spool 60% into the A position, moving the actuator at 68% speed forward. All right, and here's a little schematic of that. And you see that we have, we've applied a command signal here of positive 6 volts. That increased our current to 2.16 amps. And that moved us toward the A position. Now we're illustrating here that we're only partially in this A position by the little flow control symbols drawn on here. That will deliver flow to the motor. Flow coming from the motor gets metered out by the valve and goes back to tank here. Okay. Now, we said we'd talk about that LVDT a little bit. Like I said, there are 3 coils. We have a primary coil here, and we have 2 secondary coils. We're going to input an AC current into the primary coil, and any movement of the spool is also going to move this ferrous core, which will induce a current in one of the secondary coils. Right? If we move the spool to the left, then that's going to induce a negative output. If we move it to the right, we get a positive output. So we've shifted our spool to the left. In other words, we applied our positive 6 volts, and that generated the 1.35 amps in the coil. Right? And as the spool moved, shifting to the left, that induced a current into the secondary coils. That's going to be an AC signal. It has to be demodulated into DC to match our command voltage. So we're getting a negative 6 volt feedback and a positive 6 volt command signal. Those two are going to add up to 0. So as soon as the feedback from the LVDT matches the command signal, we stop building current in the coil, and it shifts proportionally to the command signal applied. Now that fail-safe position doesn't have to be a closed position. It can be a position like this. You see that it connects these A and B ports here, connecting those to tank, and it blocks the pressure port here. This is called the float fail-safe position. We'll use this when we're using the valve as a pilot valve for a 2-stage proportional valve. The amplifier. Once we receive our enable signal, the enable light is going to illuminate green. We're also going to be measuring the power supply voltage. And if our pilot supply voltage is too low for a Bosch valve, that would be 21 volts, because it should be 24. If it drops as low as 21 volts, then we're going to illuminate red on this power supply here, the UV is labeled. The U, of course, stands for the electrical voltage, and I'm not sure what the B stands for. Maybe one of you can tell me. All right, if we have any kind of problem with the LVDT, broken wire or out of calibration or anything like that, then this LVDT light here will shine yellow. And then we have another thing here, the zero adjust. It's a little flathead screw, and we will adjust that whenever the valve gets out of null. How do we know when the valve gets out of null? Well, it's out of null if we're applying, say, a zero command voltage. That means that our actuator should be stopped. But if it's not, if it's drifting, then we can adjust that drift out at zero by adjusting it until it stops. And usually we don't have to adjust that very much, just a little bit of a turn with a small flathead screwdriver, and that will compensate for any lack of calibration or weakened components in the amplifier, or sometimes the spring will do it. Here are the connections on your valve amplifier. Your enable output and your test spot and ground, Z32 and B32, plus or minus 10 volts for enable output, and then there's a earth ground here. Our input, plus 10 volts here. Z16, power supply, that's going to be up to 24 volts at Z22. Another earth ground here. And these are the command inputs. We're going to measure, just make sure we are in fact delivering the right command signal. We can measure that here. That'll be plus or minus 10 volts. Here's the input from the power supply, and the smoothing capacitor we probably won't have to deal with very much. It either works or it doesn't most of the time. Here's the actual earth ground here, so we can compare our ground over here with B14 and B12 to make sure that we are getting a good ground throughout the amplifier. And these are the connections to the valve. Right, you see that our LVDT feedback here, plus or minus 10 volts. And then the supply voltage that we apply, we've got a positive 15 at Z30, negative 15 at B30, and 0 at B24. Okay, and this is the current that we develop in the coil here at B6 and B8. That's where we can measure the current. So as an example for our zero adjust, let's say that we're applying a zero command voltage. Shouldn't be moving, but if it does move, that means we've shifted a little bit into this A position or perhaps the B position. In the example, we've shifted a little bit to the A, so we're going to be drifting a little bit clockwise. We can adjust the zero adjust here, and that will change the bias so that our command voltage will appear as a 1/10 of a volt, say, and our feedback from the LVDT is going to appear to be positive 0.1. Okay. A few little tips on troubleshooting the direct operated valve. The best way to do it is to buy a test box. It sounds like I'm asking to get something very expensive. Fact is, a test box costs less than a valve. That means that it's going to pay for itself the first time you don't change a good valve by testing it with the box. But you can make one yourself. You can make a test pot. We're going to show you how. We've got a little schematic included in your download materials where you take a 3-conductor cable to a return pot, and we need a value of 2 to 10K. And we can use a regular digital or analog multitester and a DC current meter. It's got to be capable of reading 5 amps to check the current signal. That will pretty much cover you with just about any brand of valve. This is the schematic. Like I said, it's you have a permanent copy there in your download. So your initial checks. First, verify that the enable light is lit and the yellow LVDT and red UB lights are both off. Of course, if that's not the case, then we know that we're either not getting an enable signal. That could be a bad wire or something. Same way with the LVDT. And if the red UV light is on, that will tell you that our power supply voltage is bad. You need to change the power supply probably. If the actuator will not move, then go back to those B20 and Z20 connections I showed you earlier and check the input signal. Before you test the valve though, make sure that the drive motor on the hydraulic pump is turned off. We don't want anybody injured by any injections. Make sure your system pressure is bled down to 0. Turn off the power supply. We don't want anybody to get shocked. And disconnect the command input signal at B20 and Z20. And disconnect the enable input at Z16. Right, this is it here. You see we're disconnecting the enable input here and our command inputs at Z20 and B20. Right, now we're going to install a jumper from Z32 to Z16. That will allow the enable signal. Right, if you get an enable signal when you do that and you don't when it's connected normally, obviously we've got a problem with the amplifier. Best thing, just change the amplifier card. Also install a jumper between B20 and B14. That will take one side of the command input connections to common. All right, connect your test potentiometer to Z32 and B32. That's going to supply somewhere between -10 and +10 to the pot when you rotate it. And the wiper should be connected to Z20. Do not turn on the power supply yet. Okay, again, keep the hydraulic pump off. Install your current meter in series with the solenoid at terminal B6. Turn 24-volt power supply on. Enable light should be on. The LVDT and UV lights off. All right, and you should see on your current meter about 1.35 amps. That's going to be the current that would be generated in the coil to shift from the fail-safe position into the center position. If you don't have any current, then probably either your cable or your valve coil is bad. Check the continuity of the cable and the continuity of the coil. You should have an impedance or resistance on your coil about 2.4 ohms on a Bosch valve. Turn your potentiometer in both directions. Hydraulic pump still off. Your 24-volt power supply is on. Your enable light on. The LVDT and UV lights off. And with the test pot at 0, check the LVDT feedback voltage with your multimeter at B24, that's the black lead, and the red lead at B22, you should have very nearly 0. 0 is where you should be when the valve spool is in its center position. Now remove the enable jumper from Z16, your green enable light should go out. If it doesn't, we're shorted inside somewhere. Again, here's the connections on the amplifier. All right, now the valve spool is going to spring return to the fail-safe position, and you're going to read -12 to -14 volts between B24 and B22. Reconnect the enable jumper between Z32 and Z16 and turn your test pot. Watch the feedback between B24 and B22. The feedback should increase and decrease. If it doesn't, more than likely your valve spool is stuck. Okay. Any questions so far? Okay. Now, like I said, the direct operated valve has very small ports. It can only be used for relatively low flow applications. For most applications, we're going to require a two-stage valve. So this is a common looking Bosch two-stage valve, and you see the direct operated valve mounted on top and a much larger hydraulically piloted proportional valve on the bottom. Each of them have their own LVDT and feedbacks. The valve spool in the main spool also has a tail on it, right? And it's very similar to the arrangement on the pilot valve. We have another ferrous core over here at the end of the tail, and it is centered in between an LVDT, just like the pilot valve is. All right, now here's a little schematic of an externally piloted and externally drained two-stage valve. Like I said, whenever we're using the single stage or direct operated valve as a pilot valve, we're going to use a float fail-safe position. Right now, why do we use a float fail-safe position? The reason is because if we had a power failure or a broken wire or something like that, we would like for the main valve spool to shift to its center position, whatever type center position the valve has. This particular one has a closed center position that blocks all four ports to the actuator and to the pump and to the tank. The two springs move the spool to its center position whenever we release pilot pressure from the main spool. Right? And you see that we're connected to an external drain line over here. We have pipe plugs that are blocking the internal pilot and drain lines, so that whenever we shift into this float fail-safe position, then any pilot pressure on either side is going to be bled back to tank. It bleeds relatively slowly. We don't want it to slam into its closed position. So you see the little flow control symbols drawn in here. That means that it's not going to just slam closed and break something, but it will slow it down and then rapidly bring it to a stop. Right, so here's our two-stage operation. See, we have the pilot valve using a float fail-safe position, the main spool here. Each of these has an LVDT feedback read by the amplifier. And if we apply a positive voltage to the pilot valve, say a positive 5 volts, then that's going to move the valve spool halfway into its A position. And it will take pilot pressure and apply it over here to the main spool, and it starts shifting the valve toward its A position. It will continue to shift until we get a negative 5 volt feedback from the main spool. Once that happens, once we get our negative 5 volt feedback from the main spool, then our amplifier is going to shift the pilot valve closed and stop shifting that main spool. That's the basic way that they operate. Inside, so here's our direct operating valve, just like we looked at before, and you see the LVDT here, the coil here, and the valve spool here. And this is the main spool right here, so that we can move a much larger amount of flow and operate a larger actuator or move something very fast. And we also have an LVDT on the main spool to feed back the main spool position. Now, this particular valve has been configured to be externally piloted and or drained. Okay, and that's done by these pilot pressure plugs. When we order these valves, we need to know whether we're internally or externally piloting or draining the valve, and we have to order it configured that way. Unfortunately, sometimes we'll either order the wrong thing or we'll order the right thing and the wrong thing will get shipped. The valve is going to look exactly like the valve that came off, and because it will be exactly the valve that came off, but it won't have the pilot plugs installed properly, right? If we need to be externally piloted, that means that we need to have pilot pressure supplied externally through this port right here, the X port of the valve, right? That means we have to block off the internal pilot line that gets pilot pressure from the P port of the main valve. And if it's going to be externally drained, we need to drain through the Y port, meaning that we need to block off the port that comes from the tank line, the T port here. Have to block this port off so that we don't drain through the main spool. We need it to drain through the Y port. If it's meant to be configured for internal pilot and drain, and it comes back with these plugs installed, then when we install it, it's not going to work. We won't be able to get any pilot pressure, and we won't have anywhere to drain the pilot valve. Okay. So before you go sending it back and wasting a lot of downtime, remove the pilot valve and look down in these ports and see if you see the pilot plugs. Right? These little plugs, typically they're going to have a little Allen wrench hole in there, and you can screw those out if they're supposed to be out, or you can screw them in if they're supposed to be in there. This could save you a significant amount of downtime. I had one student in class that told me, had he known this prior to the event, he could have saved his company 8 hours of downtime at $12,000 an hour just from sending valves back to the to where they buy their valves and getting replacement valves. So these two little pilot plugs cost them $96,000. Obviously, the company made good on the valve that was shipped inadvertently, but they didn't pay for the $96,000 of downtime. So that's why I kind of mentioned this. Right. So when the valve is shifted to its A position, see that our pilot valve is shifted to its A position. Pilot pressure comes externally through the X port and is directed over here to the main spool, shifts the spool to the left. As the spool shifts, the core moves inside the coil and delivers a feedback signal for the amplifier to read. And as it shifts, oil that's in the chamber over here on the left side goes back to tank, through the pilot valve, and over here out the Y port, back to the tank. Right, now system flow is going to come in the A port and go out of the P port, and goes out to move the actuator, moving it forward. Coming from the actuator to the B port, and it gets metered through the partial opening of the valve spool back to tank this way. Okay. Now, if we're going to internally drain the valve, then we'll have to remove that plug, right? That instead of directing to the Y port, then it will go to the internal drain of the valve. On some valves, by the way, we have to take it out of the chamber and we have to screw it into this Y port. And same thing if we want to externally pilot. We have to remove the plug here, and again on some valves we have to screw it into the export here. Okay. So if it's internally piloted and drained, it's shown on this schematic. And you see that we show the pilot pressure being derived here at the P port of the valve, and the oil that drains back out the T port. So we have our plugs removed, and now our valve is going to be internally piloted and drained. Plugs are gone, and so pilot pressure gets delivered here, and oil that drains from the pilot valve drains out here. When you're troubleshooting a two-stage valve, check the pilot valve first. Okay, we need to know that the pilot valve is okay first. When the pilot valve, and the pilot valve is the direct operating valve, and we've gone over the procedures for checking the pilot valve. Once you've checked the pilot valve and confirmed that it's good, then turn your test spot to 0, make sure that everybody's clear of the machine, and turn the pump on. Turn on your power supply. Make sure your enable light is on. The LVDT and UV lights are off. Put the multimeter on B28, the black lead, and B26 for the red lead, and with the test spot at 0, feedback from the main spool LVDT should also be 0. Okay. This is the two-stage valve connector amplifier. That shows where you can measure the feedback. This is your LVDT feedback here at B22. Turn the test spot knob while you're watching the machine operate. Now the feedback should increase as the cylinder or motor speed increase. The signal should drop as the test point is rotated towards 0. If the load is not moving and the pilot valve is okay, obviously the main spool is not shifting. Now this could be caused by contamination in the valve spool, or you could have something plugged in the internal pilot and drain lines. If it's a brand new valve, make sure those pilot plugs are configured the way they need to be. Some valves have integrated amplifiers. A lot of people have different opinions on those. My own personal experience with them hasn't been very good, but I know a lot of people that they think they're the best thing since canned beer. So I'll leave that up to what everybody else thinks. Personally, what I've found is that on a valve that is on the machine, subject to all of the dirt and the heat and the vibration and all that, is just, to me, not the best place to put a sensitive PC card. I know a lot of people disagree with me. It's good to have everything all in one place, so that when you're troubleshooting, you eliminate your troubleshooting time, because you know something's bad. Well, just change the whole thing. Well, there's a lot to be said for that. But to me, that's just not the best place. The place for an amplifier card, to me, is in a cabinet where we have some sort of control over the temperature and the cleanliness and all of that kind of thing. But if you like onboard amplifiers, that's just great. Troubleshooting is going to be the same. Your test ports and all are going to be the same. Download the information from the manufacturer of your valve and go by what they say. In our example, though, our valve is in its A position, And since we've moved our pilot valve over to its A position, that's directing pilot pressure from the export and over here to the chamber, shifting the spool to the left. The spool gets shifted to the left, and oil is directed back to take out of the chamber over here through the Y port. And our LVDT has moved inside of the coils, and we're feeding back a negative voltage there from the feedback. Sometimes they get out of adjustment. On the side of the valve, we have a little Allen screw adjustment, and that controls the centering of the LVDT. Now, when we appear to be drifting, when we're not supposed to be moving, always use the zero adjust first. Don't go to this mechanical adjustment right away. This is sort of a last-ditch effort, if you will, before sending the valve off to be repaired. Okay, this is what that adjustment looks like. This yellow Loctite here, it's on there for a reason. If you can make this adjustment and clear the problem up, be sure to put some more Loctite on there, because it will certainly vibrate out of adjustment very quickly if you don't. But you see that what that does is turn to worm gear, and this is going to rotate and move our, go back to this picture here, that will physically move the coil back and forth to center it over the core. All right, here's a common test box. This is a universal test box that you can buy. It has a slot here where most amplifiers will fit, and there's different settings that you make over here for different brands of valves. And these are the different adjustments there. I'm not going to go over that. We're getting a little bit short on time, but we do have in your download all of the information on all of these. Does anyone have any questions?
All right, Jack, thank you very much. At this time, we will leave it open for any questions at all. Okay, let's see here. All right, it looks like we have a few, but they'll be better answered via email.
Okay.
This recording. All right, so thank you again so much for presenting there, Jack.
Well, thank you for having me. I look forward to the next one here.